Okay, welcome back everyone. We're going to take a look at how we calculate energy and work and power in rotating systems. And we're also going to take this opportunity to do a little bit more practice using net force and net torque. So that's our essential question. How do we calculate work and power for rotating objects? But as mentioned, here's our example problem. And we want to calculate the acceleration of the system, as well as the magnitude of the tensions T1 and T2. So this is the pretty much exact same thing that we had before. We are going to quickly draw forces. So we have M2G and T2 on block M2. We are going to have, let's just call it M1G sine 30. We can jump to that. And T1 and F normal, and this will be M1G cosine 30. And then for the pulley, we will have T1 and T2, both of which act at a right angle to their respective radii. And so we can just go ahead and write our equations for them. Okay, we're going to assume that the system is accelerating down. As it turns out, even though M1 is bigger, it's not that much bigger. So we're going to assume this is the direction of acceleration, and it'll angularly accelerate in the counterclockwise direction. So therefore, what we have is for M2, we would have M2G minus T2 is M1A. And for M1, we would have T1 minus M1G sine 30 degrees. Whoops, that should be a 2 right there. Just caught myself. So that's M2A. You're probably yelling at your TV screen, computer screen. So that's equal to M1A. You're yelling, Mr. Dubrow, why did you mess that up? Okay, and then we would have for the pulley, basically T2R minus T1R is equal to I alpha, but we have the same expression as before for I, because it's a disk, and also for alpha. So again, those R's cancel, and you get T2 minus T1 is equal to 1/2 MA. Okay, so at this point, the algebra is really not that important. It's just the setup here. And so if you're curious for checking your answer, acceleration is about 1.3 meters per second squared. Okay, so now let's talk about the concept of equilibrium. So equilibrium occurs when there's no net force and no net torque. All right, static equilibrium is when there's nothing moving or rotating, and dynamic equilibrium is when we're moving or rotating but at constant velocity. So here are conditions for equilibrium, and this one for force can actually be turned into X and Y. Okay? All right. So a quick example problem. Mary has a mass of 60 kilograms and is sitting at one end of a 3-meter long board of mass 10 kilograms. Bob has a mass of 75 kilograms and is sitting at the opposite end. Where should the board be supported in order to balance Mary and Bob in the air? Okay, so Mary is at one end, Bob is at the other, and we want to know where to put this balance point. Okay, so basically we can call this distance x, we can call this distance 3 minus x, and we know that the board itself, which now has a mass of 10, is going to have a force of gravity in the middle. Okay, so Mary will have a force of gravity of about 600 newtons. The board is going to be about 100 newtons, and Bob is going to be about 750 newtons. Okay, now there is one more force, and that's going to come from where the board is being supported, and that's going to be a normal force. And so we actually have two equations that we can set up here. We have a torque and we have a force equation. We don't have any x forces, but we can say that the sum of the y forces must equal 0. So 600 plus 100 plus 750 are all going downwards, and they have to add up to equal Fn. So Fn must be 1450. Now we can use that with the sum of the torques equaling 0 in order to calculate the pivot location. So that's x that we're looking for. Okay? And so let's just say that, just for simplicity, that this point right here is x equals 0 at the left end. Okay, so the torques, and we'll say that a torque that causes counterclockwise rotation will be positive. So it looks like the normal force is going to create a positive torque that's equal to the normal force times that distance x. The weight of the board, which is 100, will cause a negative torque at a distance of 3 minus x. And the weight of Bob will create a torque with a force of 750 newtons at a distance of 3 meters that will also be negative, and those must all add up to 0. Okay, now this normal force we can substitute is 1450, so we can just solve this. 1450x minus 300 minus 100, plus 100x minus 2250 is equal to 0. And so that means that basically 2550 is equal to 1550x. And so x here is going to be equal to, let's see here, 2550 over 1550 is going to be about 1.65 meters from the left edge of the board. Okay, now we can talk about work and power. So in a system that's translating, moving in a straight line, it's just force times displacement. And we're going to substitute torque and angular displacement, and we will get work in a rotational system is torque times angle. Now if you remember that torque is force times radius, and roughly speaking, delta theta is S over R. Okay, this is kind of like delta S here. Then if you multiply those two together, you're going to get basically F times S, which is what we had. The R's will cancel. So that makes sense. And now we can think about the fact that different kinds of work will change different kinds of energy. So the net work is for delta K, conservative is equal to negative delta U, and non-conservative is equal to delta E. So this is a very important idea. Okay, power. Power is dW dt, so it's the rate at which work is done. So it's F dot V. And if we just substitute torque and angular velocity, we get power is torque dot angle. Okay, now we know that power is in essentially watts, which is joules per second. And so torque is newtons times meters, and omega is radians per second, so that is joules per second. Now one thing we forgot to mention, going back to the previous slide, is that when you take torque, which is newtons times meters, and you multiply it by an angle, which is radians, that will finally get you to joules, okay? Because technically, there's kind of like a latent radian down here that's not really being discussed, but it's there. Okay, so our conservation of energy tells us that in either a rotating or a linear system, we can just add up the sum of the potential and the kinetic energy. Okay, so here's an example. A rotating flywheel provides power to a machine. So here's that flywheel. And it's initially rotating at 2,500 RPM. And we know the conversion for that is times 2 pi over 60 to get into radians per second. Okay, so the flywheel is a solid cylinder. So I is 1/2 mr squared, and it's got a mass of 1,250 kilograms, and it's got a diameter of 0.75, so a radius of 0.375 meters. And if the power is 12,000 watts, how long can the flywheel provide this power? Okay, so it seems like there's a lot going on here, but we just want to start with the basic definition of what power is, because we're going to use power to get to the torque. Okay, power is torque dotted with angular speed. And then our next step is to use the fact that torque is equal to I alpha. And then our final step will be to realize that alpha will be delta omega over delta t. And that is how we will ultimately solve this for the time. Okay, so power is 12,000. And that's going to be equal to torque times 2,500. But we have to turn that into radians per second. And using our conversion up here, 2,500 times 2 pi over 60 is going to give us 262 radians per second, and that's watts. So this means that the torque is about 45.8 Newton meters. Now, torque is equal to I alpha. So 45.8 Newton meters is going to be 1/2 m r squared times alpha. So this means that alpha is going to be about negative 0.543 radians per second squared. And finally, we know that omega final is equal to omega initial plus alpha t. Another way of rewriting this equation. Omega final will be 0, so 0 is equal to, we'll use omega initial as 262 radians per second, plus negative 0.543 radians per second squared times t, and we will get our final result for the time, 262 divided by 0.543, or about 483 seconds, which is just over 8 minutes. Okay, let's do one more example. So now we have another rod of mass m and length L that rotates around a pin through one end. So we did this in a prior segment, and so it's going to be released from rest at horizontal, and we want to know the angular speed when it reaches the lowest point. So when it is vertical like this, we want to know omega, and we want to know v of the end of the rod at this point. Okay, so using conservation of energy, we know that energy initial must be equal to energy final. Now energy initial, if we set this up in a smart way, we can say, that H is equal to 0 at this point. So that means that potential is 0, and it starts from rest, so kinetic is 0. And then final, well, it's going to have potential final plus kinetic final. And that kinetic will just be made out of the rotational. Okay, so 0 is equal to negative mg L over 2, because now the height that it's going down to is L over 2. Now this is important. I'm using potential energy of the center of mass of the system. And that's how you deal with an extended object. You look at what happens to the center of mass. Kinetic energy, you also look at what the center of mass is doing. Is it moving in a straight line or is it rotating? And in this case, it's rotating in a circle. So we don't have 1/2 mv squared, we just have 1/2 I omega squared. Okay, now I is 1/3 ml squared. So we plug this in here, okay, and we get mg L over 2 equals 1/2 times 1/3 ml squared times omega squared. M's are gone, 2's are gone, L's are gone. So omega squared is 3g over L, or omega is the square root of 3g over L. Okay? Then we make use of the fact that to find the speed at the lowest point, v is equal to omega r, but r is L at the lowest point. Sorry. And so we just take square root of 3g over L times L, which is basically root L squared over, hold on. It's just times L, okay, which is root L squared. And that means that this is root 3GL. Okay, now each of these are dimensionally correct. G over L will be radians squared per second squared. Okay. And V will be in meters per second. Okay, so that wraps it up for this segment. In the next one, we are going to look at rolling without slipping.